introduce our keynote for today. Lukasz here from OpenAI and also one of the co-inventor for Transformer and TensorFlow. Lukasz is deep learning researcher right now at OpenAI and previously was at the Google brain team. He recently worked on GPT-4 and the Codex model. Earlier, he also working on a variety of machine learning algorithms and also model before it. So without further ado, Lukasz, you're on stage.
Can you hear me? Oh, I think so. And I did. So I thank you very much for the invitation. I came to speak a little bit about the history, but I'll try to go quickly. So we maybe have 5 minutes for questions later. So you know, when I started deep learning, that was about 10 years ago. I came to the Bay. I had nothing to do with machine learning before, so that was my new thing. And I started in parsing. I was hired at Google to do parsing of language into trees, and around that time, there were well, it's super slow. Okay. Yeah, there was this paper, Sequence-to-Sequence Learning with Neural Networks by Ilya Sutskever, and this paper I think was a motivation to a huge field, because before that, you know, neural networks were already used, but they were used for images. They were like, okay, you can tell whether there's a cat, which is great, not to generate, right, to just tell what's on it. But this paper was kind of the start of like, well, you can give it a sequence and get out a sequence. And you know, in computer science, everything's a sequence. It can be text to text, so this was for translation, but it can be text to image, image to text, like audio, whatever, right? And this one was based on RNNs. So RNNs are a different kind of neural networks than the ones we're using today, but it was still a shock to many people that you can train this neural network, which may look a little complicated, but it's like a half a page of formulas, and you just train it with a lot of data, and it will learn to translate from English to French. We were all astounded. That was the case 10 years ago. And the translate team at Google, they were like, nah, it won't work very well. It's just a one-off, it will plateau, it won't do other languages. So they were like, yeah, should we really use it? Like, we don't know. But I was like, well, wait, if it can translate from English to French, it must be able to do parsing, like translate English to a parse tree. So my first paper in machine learning, that's the whole paper, right? It's like, if you have a tree, you can actually write it with brackets. Everyone knows that. That's the whole idea of the paper, and you run the same network on it. Now, it took a year at that time to put up the infra to run the same network. But that's still a little hard, so that was the real work. But you know, lo and behold, it turned out the networks can parse too. But then, like, okay, so they can translate, they can parse, so maybe we should make them better, right? Because before it was like people did not believe they can do anything. So the translate team, luckily they were quite good colleagues with us, so we were like, come guys, let's give it a try. So we gave it a try, and it turned out the RNNs, so this was LSTMs, can give like a huge boost in translation in all their languages. So like, okay, no, it actually works. But it was slow, and it was like one sentence level it worked well, paragraph level it didn't. So we came up with this other architecture that's currently powering a lot of the models, which is called the transformer. And the transformer is a bit different from the RNNs, because the RNNs go like word by word, very sequential. The transformer, it has something called the attention layer, so it looks at all the past at the same time. So here on this picture, like the arrows are what it looks at. And the great thing, there's a few great things about that. One is that it can run totally in parallel if you have the whole text. So training is extremely parallelizable. It doesn't need to do any sequential steps in training. It just has this cross-attention matrix, which is n squared, where n is your length, but your length is never that big compared these days to your matrices. So it runs really fast on GPUs and TPUs, so that's great. But the other thing is, it can look into the past with one hop, right? So these gradients that need to flow through this network and learn, they can jump into words that are way, way, way in the past and learn whatever pattern they need to learn from that. And that's what all our language models are based on. But the first thing we tried it on was translation, and even on translation there's this metric called bleu. When I was a PhD student, they were saying like if you get 2 bleu improvements, you get a PhD, something like that. So 20 was the bound on English, German. Then like the really good networks were 23, right? At the time, this was only RNNs, the normal systems were like 21. And then like you could push it to 25, and then transformers came at 27, and then you improved to 29 when you made them a little larger, and 31 is what human translators get, and we're long at this level, right? But okay, so we had a great network to translate, success. But then other things came, and I think the 2 years after, the biggest discovery was this supervised pre-training. And I think BERT was the first paper where BERT and GPT at the same time, where people noticed, wait. Like instead of doing this, we gather data for translation, because the data for translation is like you have a corpus like the European Parliament, you have sentence by sentence correspondence, this is in English, this is in German, you gather a lot of data. The same for parsing, you have a sentence, you have a parse tree, you train on it. This was what ML was about, right? Gathering training data. Now, then came the supervised pre-training, and it said, no. Just take the internet, train all of it to predict the next word. Or maybe in case of BERT, mask out a few words and predict those. So at that time, that seemed like a very weird idea, but it worked extremely well, and you could do the same for images, right? You could train on you have a captioned image on the internet, take the caption, predict the image, and then it would be able to do something like draw a baby daikon radish with a tutu walking a dog. So why something like this? Why an armchair in the shape of an avocado? Because that's something that has never been found on the internet. So these models, they don't just memorize the internet, right? They find like some understanding of what's happening there, and they can draw it. And that, to me, that was the surprise of these years, right? We've learned that the models can translate with the right data, they could do this really well, but now it turned out that from this totally random hodgepodge of data that's the internet, they can actually understand what's happening. So maybe we could have this one model just trained on the internet that you just ask it to do stuff. And it started with GPT-2, and already at the GPT-2 level you could show like hints of it. So GPT-2, it was interviewed in The Economist at some point. It could generate like a 2-sentence answer that was reasonable. But then it turned out, yeah, maybe you just make it better and you get something called GPT-3. So that was the paper. And to build GPT-3, you need to realize a technical issue. If you're training, like normally in the ML4, it was like, yeah, you're training a model, but you'll make 10 runs, like pick the best learning rate, pick the best initialization. You always run like 10, 20 runs of the model and you like tune something. If your model costs $100 million to train, you're gonna run one run. So you better know every single parameter how to pick it, but you don't know. Like this is totally, this is like, deep learning is like mixing this pile of sand, right? How would you know? Well, so the scaling laws tell you how to know, because it turns out you can, if you train a lot of small models, and they just increase in size. So here, every of these blue lines is a training curve of a model, and the size of the models is increasing. So it's clear the ends of this curve form a line, right? So you know, if you want to train a bigger model, you know where it should be if you're doing things right. Or at least if you're doing things in the same way as the small models, because you don't really know what's right, but with the small models you can test a lot of things. So this tells you how to train, how to get parameters, and so you can train a model like GPT-3 that can start telling you long stories. and fun things. Like you can just play Dungeons and Dragons and it will make up stories and it's coherent and it does nice things. But the interesting thing is you can start telling it, hey, could you translate English to French, this sentence to that? You give it 2 examples maybe and it starts translating. And that was a shock. Like around that time, people were still writing papers asking, is it even possible to learn translation without pairwise data? And I was like, yeah, unsupervised translation may be a goal, maybe it's possible, maybe it's not. This is like, I mean, maybe somewhere on the internet there is a few translated sentences, but it hasn't had any pre-prepared data, right? And it has learned to do that. And you see that there is a big jump with just scale of the model. And, you know, New Year's came, the data improved a lot. So there was a lot of work in data cleaning. A little bit of RL started being put, so this is the ChatGPT slide, where you don't just pre-train the model, you also RL it a little bit to do what people ask it to do. And, you know, so when I did parsing, you had to gather this parsing data, and there was not enough of it, so you had to like produce it, but it was a lot of work. With GPT-4 and chat, you just say, hey, do you know what constituency parsing is? Oh, okay, I know. Could you parse John as a dog for me? Okay, it's a perfect parse. It has never learned constituency parsing. It made some book on the internet, but it's just a mixing in a file. And it's not just like this sentence, you know, it can like, it explains you what all of this means if you don't know. Like you ask it. I chose a sentence from the New York Times like a few days ago. I asked it, you know, it's a perfect parse. No problem. So tasks that used to be like, you need to hire researchers, gather data, train models, you just ask it and it does it. Translation, you know, can you translate from English to Polish these paragraphs? Okay, here is your translation. It's actually a little better than Google Translate, I would say. You know, there's this table with exams that it can pass. So it actually learned. It actually understands not very advanced concepts yet, right? But it understands what's translating, what's parsing. And parsing is not a broad concept that you know. Translating, there is a lot of it on the net. Parsing, law, there's not that much of it, but it has learned. So that was quite magical for us. Like, these models, they have really generalized. From this pile of very dirty data, they had managed to extract some knowledge and understanding. That's quite amazing. That's why all of the AI is around here. So what's coming? And I mean, so this is a little bit of a technical slide. The key to all of this miracle is that these things just generalize. It's very easy to store the whole internet on disk. It's very easy to memorize it. You can build a trie tree and it will should tell you what's the distribution of the next word on the internet, but it will not tell you anything you need to know because it doesn't generalize. So how do these neural networks generalize? How does this miracle come to be? We don't really know. That's the problem. But what we do know is that gradient descent is one piece of this miracle. So this fact that you have these trillions of parameters and do gradient descent of them is important to how the network processes the data. And what you need is an architecture that's really powerful. So a transformer is more powerful than RNNs and it unblocked a lot of these things. And you need to figure out how to do this gradient process well, which is not trivial, but now we have some knowledge about it. But, okay, so these two ingredients give you something that generalizes. Could we make them even more powerful? Could we get things even better? Like, could we build a network where you just show it 2 times to do something and it somehow understands and learns on its own? So, you know, the transformers, one of the hints was in this early RNN paper, you could see that when you added attention, it started learning from much less data. So if we had something that learns from even less data, but gets very good results, that would be impressive. So how would you get that? Well, if you think of the theory, you need to make your neural networks even more powerful than the transformer. And it's not quite clear how to do it. But, well, one thing that they could do would be to add recurrence. And people have tried to add recurrence in depth, like universal transformers, Albert, and it helps a little bit, but it's really tricky. And it's very inefficient, so we don't train big models like that. But the flip side of adding recurrence and transformers in depth is you could just let the model put some tokens out. And this is called chain of thought mostly, and called chain of hindsight, and programs of thought, and so on. But I think this has turned out to be the method that makes transformers more powerful, is you just let them rumble around a little bit. And so what is chain of thought? Like if you have a problem, say your order has 5 tennis balls, he bought 2 more, how many balls does he have now? Instead of saying, well, give me the answer now, like the token 7, you say, hey, think about it, give it some thought, generate some thinking, and then give me the answer. And at least on mathematical questions, this gives like insane gains. And insane is the fair word to use. Like if a transformer has a limitation in running time. It runs in n² time for input of like n, and that's it. When you allow it to produce chains of thought, it's as computationally powerful as anything you can imagine. And there is a recent paper where it actually like simulates long programs. So this way of using the network has immense power, but we don't know yet how to train it to do this well. So it's a very powerful network, but since you can't propagate gradients to these tokens, you don't know how to bring the miracle of stochastic gradient descent to this yet. But, you know, if you ask the model to do like step-by-step mathematics, and you train the verifier, like you can get like 78% on a data set that was especially designed to not be solvable by GPT-4. So there are early signs of success. There is something that just builds a knowledge library in Minecraft of these chains of thought. So I think we're moving to a world where these thoughts of the models, they become the foundation of learning. I mean, parameters are still important, but the tokens that come around them become what the models need, what is important. They may be grouped into libraries, they may be retrieved with retrieval. So we are slowly but surely moving past the paradigm that you have just parameters that you train with gradient descent towards a paradigm you also can have tools. Like you can say, like if you ask for distances, you can go to Google Maps, Google it, get an answer, so tools are involved in this too. How do we learn in this paradigm? Well, currently we learn with RL. So we train the model, gives good answers. We use RL to move on. Do we know whether the model is giving true answers? Well, that's becoming the question. You have all these tokens, the model has done some explorations, it used some tools. Is it giving you the truth? Now, what I want to tell you is the truth is a very difficult concept. This is a sentence that you would say is true, but for a bunch of centuries, people did not think of it as very true. There was a book that was defending this. It has a few hundred pages of a very elaborate chain of thought, written by a man who's by many considered one of the smartest men ever alive. It's good to know 1/3 of this book was totally false. It had a theory of tides that we know is absolutely false. Tides are not caused by the sun, they're caused by the moon. Nevertheless, the main premise of it is true. So truth is very difficult. And you see, even one super bright mind may not reach the truth. Because if you really want to know whether complex things, I mean, mathematics is a little bit of a special case. You can very much verify it formally. But truth in the broader setting really needs a community. Like, you need AIs and people to discuss things, to put some stake into things maybe. It's a very complex concept, but it really hinges on a community discussing it. So what I believe is that the biggest, like, it's a new world that's coming, right? The big models, yes, they're part of it. They're important. They should be there, big and small, and then fine-tuned different kinds of them.
But what will really start mattering is this library of knowledge that they create, the discussion and debates they have, the tokens that are produced here and there. And some of them will be bad and some of them will be good because you can't know which ones are which until you start running like a process of debates and discussions. But we really don't know how to do this very well. We somehow do this as humans in a society, but it's very messy already, and with the models it just scales up and gets super messy. But we'll need to figure this out because this is the only way we'll go forward. So as nice as it is to build the open source models in the sense of parameters and training, and it's important and good, really think of this, how can you build like agents that use models? And they can be open or through an API, it may not matter all that much. How do you build it? Like, how do you take together all the generations and make something that's really smart out of it rather than just a lot of text that's not used? We don't know yet, but I think this is something that we'll need to solve, and